Let's have a look at the mechanism for the electrophilic addition. This is the halogenation of an alkene. This can either be the monohalogenation using a hydrogen halide or the dihalogenation using a halogen molecule. Before we get into this mechanism, let's recap what an electrophile is. So you should remember that an electrophile is an atom or group of atoms that is attracted to an electron-rich centre and accepts an electron pair. Alkenes contain a carbon-carbon double bond, which you should remember is made up of a sigma bond and a pi bond. Because of the pi electrons, this area around the carbon-carbon double bond is described as being electron-rich. Let's have a look at the monohalogenation. For this example, I am going to work through the bromination, but this can also happen if you have hydrogen chloride. So let's have a look at the hydrogen bromide molecule. You should remember that bromine is an electronegative atom, which means when it is bonded to something less electronegative than itself, it holds a greater share of the electrons in the covalent bond. So we describe this atom as being electronegative, and we describe the other atom, in this case the hydrogen, as being electropositive, because it is deficient of electrons. The electrons can move from our electron-rich centre to our electron-deficient hydrogen. We're going to show this using a curly arrow. Remember when you draw your curly arrows that we need to be precise. So you must ensure that they touch the bond that is cleaving and they go to the atom that is gaining those electrons. Because the hydrogen has just gained a pair of electrons from this electron-rich centre, the bond here heterolytically breaks. And the electrons are given to the bromine atom, forming a bromide ion. We also at this stage form our carbocation intermediate. Because we have a symmetrical alkene, it doesn't matter on this occasion where we put the hydrogen. But if you have a non-symmetrical alkene, you will need to consider Markovnikov's rule to work out which is your major and minor product. So on this occasion, I'm just going to put the hydrogen on the left-hand side. This carbon here is electron deficient, so it has a positive charge. We are now going to form a carbon to bromine bond, where the electrons move from our bromide ion to our carbocation. You can show this with a curly arrow going from the pair of electrons to the electron deficient centre here, and we get through to our final product. Let's have a look at how this mechanism is different when we dihalogenate. So this time we have two atoms that have got the same electronegativity, but because this is an electron-rich centre, as the bromine molecule approaches it, the electrons are shifted in this covalent bond, and they're shifted away from our electron-rich centre, which makes this bromine delta positive and this one delta negative. The rest of the mechanism is the same as before, but we'll go through it just to make sure we're happy with it. So again, the electrons move from our electron-rich double bond to our electron-deficient atom. This then causes the heterolytic fission of this bond between these atoms, and we form a bromide ion. Again, we form a carbocation intermediate. Where we have our carbon, which is electron deficient. We then have the formation of a new covalent bond between the bromide ion and the electron deficient carbon. You can also show this curly arrow moving from the negative rather than the lone pair of electrons, like so. But remember to make sure your arrow is precise. And this time we get through to our dibrominated product.